I'd like to introduce to you Ron Polidon. He's an astrophysicist, space technologist who retired and moved to Terrebonne in 2016. He unretired in 2020 and currently holds the position of Director of Programs at Lunar Technologies, Inc., a space industrialization company based in Houston, Texas. He is leading a NASA-funded study to develop a detailed concept for a very large radio observatory, larger in area than the city of Bend, that would be robotically built on the far side of the moon using materials extracted from lunar dirt. The primary science goal of this observatory is to see back to the dawn of time beyond what we can be observed with the James Webb Space Telescope to before the first stars in the universe have formed. He has over 45 years of space mission experience, working almost equal amounts of time in academia, government, and industry. His previous two employers were NASA Goddard Space Flight Center and Northrop Grumman Aerospace System. At Goddard Space Flight Center, he served in a variety of roles, beginning as NASA's project scientist for operations for the Hubble Space Telescope from prior to its launch to 1990 up to the first Hubble servicing mission, and ending as the NASA's chief technologist, overseeing all technology development in the NASA Center. Ron, just so everybody knows, when Ron and I joined the webinar earlier, it was like, Ron's no joke. He is the real deal. So I know he's got some really great information to share with us today. So I'm going to invite Ron to share his screen, and he'll talk about how he's going to address questions and answers.
All right. Thank you, Liz. Let me share my screen. All right. As I said, good afternoon, everybody. My name is Ronald Polidon, and today I'd like to talk with you about our place amongst the stars. And what I mean by this is I'll discuss how humanity determined the scale of the universe, what it's made of, its age and evolution, and how we fit into all these things that we see around us. This realization of where we fit amongst the stars has altered human society a good deal and shaped who we are. This is an outline of the topics, four major areas, prehistory to the 30s, then the modern era, then life, and then future expectations. I think it's important, I want to start with the history because I think it's important to understand how we got to today's knowledge. Then I'll provide you with a discussion of the vastness of the universe and its content. And people always underestimate how big the universe is. Finally, I'll talk about life and what's going to happen in the future. Another theme that's woven through this talk is that these discoveries were not achieved with a slow and steady progress. Instead, its progress was made through the astrophysical equivalent of punctuated equilibrium in evolutionary biology. Long periods of stable knowledge with minimal changes, interspersed with small major events of understanding that changed our perception of what the universe was. And the reason I want to do that is this is how astrophysics works, but also we are at the beginning of one of these stages where our whole view of the universe is going to change. So over the next 10 to 15 years, I expect we will greatly alter what we perceive the universe to be. Because this is in four sort of independent sections, what I'm going to do with the questions is at the end of each section, I will stop and ask for questions on that section. And then at the end, obviously, you can ask questions on any section you want. So let's get started. So from prehistory to the 1930s, from at least Neolithic times, we've looked at the skies with more than just wonder. They were analyzing the sky. These were actually very smart people. People tend to think early humans were not very smart. They were very smart. They didn't have our technology, but they did have a lot of time. And in the center image at the bottom of the chart, you can see cave art from 15,000 BCE with some dots circled. Archaeologists think those are a representation of the Pleiades. And there are other dots in this cave that also look like other constellations. So at 15,000 BCE, it looks like someone was actually looking at the sky in detail. But the major reason for the early humans to study the sky was really timekeeping and seasonal changes. They didn't have knowledge of the calendar. And so in order to know when to plant, when to harvest, when to do other things, they realized they could rely upon the stars and their motions to do that. And so this measurement system that they used of just tracking the stars allowed them to determine the length of the year, when seasons began, times to plant, times to harvest, etc. And we find these calendar circles throughout the globe. One of the oldest is shown on the lower right, the Nabta Playa. This is in the Nubian desert, and this dates from about 7,500 BCE and is a calendric circle. So it was tracking motions. And on the left is the Nabra sky disk. This is the oldest concrete depiction of an astronomical phenomenon. And it also probably was related to calendar measurements. So early civilizations across the globe, this is not just limited to one area, developed astronomy and had fairly sophisticated machinery to measure the sky and track motions. The real superior group for this, though, were the Greeks. Their mastery of geometry and math, along with their curiosity about the structure and workings of the universe, produced our first actual measured instrument, a measured estimate of the scale of the solar system. By 200 BCE, they knew that the Earth was round. They actually had a very good measurement of the Earth's diameter and the relative sizes of the Earth and the Moon. And the picture on the lower right is how simple geometry can give you the diameter of the Earth. And they had this accurate to within something very similar to what we know the Earth to be. They also had a good estimate of the distance of the Earth and the Moon. Unfortunately, their distance to the Sun was not very good. They had it much closer than it actually is. But that was because these are some fairly small angles, geometric angles that they had to measure, and they just didn't have the technology to measure it. But they did produce the first heliocentric model of the solar system, and they produced the first planetarium. And this is the one that is usually considered our oldest version of an analog computer and a planetarium, the Antikythera mechanism. What you have on the left is the picture of the actual artifacts that they pulled from the ocean. And on the right is a modern rendition of what we think this device looked like. And if you really want to find out what it is and how it works, this site at Interesting Engineering tells you a lot about how it was constructed, and they actually have an animation of how it worked and all the various pieces and stuff. Very interesting place to browse. This is probably not a unique device. These were probably very sophisticated instruments, and they weren't a whole lot built, but it's probably more than just one. And this dates from about 200 BCE, so this is fairly old. It's what shows you that they were truly watching the sky with great care, and they were able to reproduce a mechanical device to simulate the sky. Humanity would continue to use their brains to develop new technologies, and for those time periods, advanced technologies, things like astrolabes and quadrants and amylary spheres, things that help them map the universe. And actually, some of these measurements are actually sufficiently accurate or sufficiently descriptive that modern astronomers have actually used them to reference things. Unfortunately, the great decline of Greek science and basic research techniques, we lost a lot of knowledge, and we had a decline in understanding of the universe. Their mathematical approach was replaced by ideas that were really centered more on the specialness of humans and the Earth. Humans were considered special, and the reason for the universe's existence. We were at the center of the universe. The Earth was unique and special, and the sky was perfect. Probably the most widely accepted of these was Ptolemy's concept for an Earth-centered solar system. It was dates from about 150 in the Common Era, and actually persisted as the most believed form model of the universe until well into the 1600s. And it was Earth-centered. The Earth did not move. It was at the center. Everything, all the planets, the sun, the moon, the stars, all revolved around the Earth in perfect circles. In order to match the observations of these planets, they had to add other smaller circles and even smaller circles. And so it was a very complicated mechanism, but it did work. It did predict the positions of the stars or the position of the planets. And in fact, even today, if you wanted to do this, you could use this model to predict the motions of the planets. One of the key parts of this was this big debate that was going on at the time about whether the Earth was moving or not moving. And the evidence was overwhelming on the side of the Earth not moving. And the two primary reasons that were given was that there was an absence of a steady wind from one direction. They didn't know about space being a vacuum. And the lack of observed geometric parallax of stars. They understood that if the Earth was moving, then you would see motions in the stars. What they didn't know was how far the stars really were away, and they grossly underestimated how close they were. So both those we now understand, but for them, this was convincing proof that the Earth was not moving. The big revolution came with the telescope. That was our first punctuated equilibrium event where it changed everything. The telescope was invented in 1608, but the key thing was that Galileo built a bigger telescope, a little more power, 20 power, and pointed at the sky. And his map of the moon is shown in the lower left, and his telescopes are shown in the lower right. These are on display at the Galileo Museum in Florence. And his observations changed everything. The Earth lost its uniqueness. The sky was shown to be not perfect. And as I said, it enabled the scientists to start really developing the next phase of understanding of a semi-quantitative exploration of the universe. In the past 400 years, telescopes have grown a lot, expanded into space, changed their sensitivity ranges. We now see things from gamma rays through radio waves. And to give you an example of how much things have changed, this is a recent image of a handful of telescopes. And I want to point out in particular the scale in the red box on the bottom. This is 10 meters, 30 feet. And the three telescopes on the right, the 30-meter telescope, the extremely large telescope, and the giant Magellan telescope, all these are under construction and will come online sometime before 2030. And they are truly enormous, and they will really change what we can see in the universe, give us resolution to maybe detect planets, do all kinds of things. So look for a revolution in ground-based astronomy, provided things like the communication satellites don't mess up all of their imagery, but look for major improvements in our understanding from these ground-based telescopes. So on a human scale, what is the size of the solar system? And if I were live, I would show you a little 3/4 inch diameter marble that I have that represents the sun. And so what the Earth would be this 0.004, so 4/1000ths of an inch thickness of a human hair particle, almost 8 feet away. And Mercury and Venus would be between us and the sun, but they are also equally tiny spots. Jupiter, the giant of the solar system, is a 4/100th inch grain of sand. So it's a grain of sand 40 feet away from this marble. Neptune, the last planet in the solar system, is 230 feet away from the marble. And the Kuiper Belt, which is where Pluto and all these others, little objects lie, starts where Neptune was and goes out to about 400 feet. The limit of the sun's gravitational influence would be about 150 miles away from this marble. Out there, you'll find the edge of the Oort cloud. This is a spherical distribution of dust and other debris left over from the solar system's formation. And the nearest star, remember, we're talking about relative to a 3/4 inch marble that I'd be holding in my hand, is 390 miles away, in just outside of Sacramento, California. And so there's very little between the sun and the star other than our solar system. So space is really truly empty, but also truly large. And in the bottom right, you see an image of the Earth and the Moon from relatively close, 3.7 billion miles. This is at Saturn. And you can see it's just a little tiny dot. And you can't resolve the Moon from the Earth. They're just too close together. And also remember that all this stuff is moving. The Earth is orbiting the sun at about 67,000 miles an hour, and the sun is moving at around 43,000 miles per hour relative to the nearby stars. Our universe got big again, got bigger in the 18th century. We still didn't have the technology to measure distances to stars, but that didn't stop researchers from trying to map out the sky. In 1785, William Herschel created the first semi-quantitative map of the solar system of the Milky Way using his great telescope. This was about a 1-meter telescope. And he did this by just counting the number of stars in all the directions he could see. And he assumed that all the stars were the same intrinsic brightness, and so the fainter ones were just further away. And this is his map of the Milky Way galaxy that he published. And the sun is not quite at the center, but fairly close to the center. And it's a little blob with some tendrils going off in all directions. His measurement basically made our universe a lot bigger, and it gave us the first hint that we had that we're actually living in a very, very large universe. 50 years after Herschel's map in 1838, the first measurement of the stellar parallax was made. And this is when the quantitative mapping of the universe began. Jump ahead now 130 years from Herschel. Harlow Shapley used measurements of a type of pulsating star that resides in large star clusters. And these stars change their brightness with a relatively strict periodicity. And the period characteristics relate to how bright they are. So by measuring the period, he could determine what their absolute brightness is, and then from measuring their apparent brightness, get the distance of them. So this is what he did for a whole bunch of these star clusters. And the figure on the right, the white dots, are these large star clusters. One is shown as the Hubble image above. And he found that they were scattered across the sky, but not centered on the sun. And so what he proposed is that the center of this distribution of these large star clusters was actually the center of the Milky Way. And that Herschel's map and the maps that people had generated since Herschel only represented a small portion of the Milky Way. This led to what's called the Great Debate about spiral nebulae. And it was between two prominent astronomers, Curtis and Shapley, and it took place at the National Academy. And Shapley argued that the universe was just our Milky Way, with the sun located far from the center, and that the spiral nebulae were just clouds of gas. And the picture of the Andromeda Galaxy to the right there, you can see that at lower resolution with the hardware they had at the time, they were not able to resolve stars. And so that could easily be a cloud of gas and not stars. Curtis, on the other hand, held that the spiral nebulae were actually galaxies like the Milky Way, and that the Milky Way itself was much smaller than what Shapley said, and the Earth was located near its center. So that precipitated a lot of new data gathering, and by the mid-20s, new data had come in that showed in particular that the Andromeda Galaxy was actually very far away, well beyond Shapley's size of the Milky Way, and it was composed of stars. So it was a galaxy like the Milky Way. A whole bunch of other things were found, but the net result after about 10 years of data gathering was that Shapley turned out to be pretty much correct about the size of our galaxy and the sun's location in it. But Curtis was correct about the spiral nebulae. And the realization that these spiral nebulae were enormously far away really increase the size of our universe. So that's the end of this section. So any questions from people? I don't see any hands raised. So I will continue.
Hold on, Ron. Jim Hammond had a question. Jim, could you
Jim?
put your question in the Q&A? Oops. Okay, Jim, Jim, can you put your question in the Q&A, or do you want to talk out loud? Okay, Ron, why don't you go ahead and maybe Jim will put his question in Q&A as we move forward.
All right. So the modern era. So basically, this is where we start understanding the universe. We think we start understanding the universe a lot better. And then as things, okay, we now have one in the chat. Oh, okay, that was just that. Okay. So we started off with feeling that we were growing, getting a growing understanding of the universe and what it is. But then in the last 20 years, we've actually come to the realization that we do not know as much about the universe as we thought. So in the modern era, advances in telescope size and quality of scientific instruments firmly establish many of the basic attributes of the universe and our place in it. But the next big advance came when we started opening new windows into the universe. The development of radio telescopes opened up a whole new way to look at the universe. Putting telescopes above the Earth's atmosphere expanded the human vision to gamma rays, X-rays, low-frequency radio. We could now see the entire electromagnetic spectrum and analyze the universe through all these various windows. We can also see particles, and then recently with gravitational waves, we now think we have a pretty comprehensive way of measuring the universe. And measuring all these various wavelengths, aspects, particles of the universe have been critical for our understanding. And as an example, this is what the Milky Way looks like in 10 different bands, from the radio continuum at the top to gamma rays at the bottom. And this, the human eye one is shown, it's the third from the bottom. This is the optical. And you can see that while the basic similarities are there, details are completely different. And it's this difference that allows us to really start probing aspects of the universe. I want to pause now to take Jim's question since it has appeared in the Q&A.
Yeah, so Jim would like to know. Can you read it?
Yeah, I can read it. So okay, Jim is saying that the drawings seem to be the Pleiades in the cave seem to be a stretch. Yeah, there is debate over that. And so there are others in there that are similar. One group looks like the Belt of Orion. There's a couple of other places, but yes, this is by no means a given fact. The majority seem to be, well, I would say a plurality seems to be on the side of saying this is probably the Pleiades, but it is far from proven. So yes, you know, a bunch of dots doesn't necessarily make a constellation. And like I said, the aspect of that is there are other areas that people have pointed out that look like other parts of that same part of the sky. It's just not widely accepted. And his thing is this the case of anthropologists, as usual, making up facts? It's hard to say. Pleiades are pretty distinctive, and similarly, the belt of Orion is pretty distinctive. So the things that they're pointing to would be very prominent in the sky. But yes, there's no hard evidence that these are actually constellations. All right, moving on back to the modern era. Um, so how about today? This is our galaxy. So we live in a medium-sized barred spiral, and there's the bar. It's a reasonably common galaxy. The bar is a product of the density distribution in the disk. It produces these bars, they come and go, and it also produces the spiral arms. So all the structures that you see here are due to all the various stars and gas clouds in the disk of our galaxy. This is a simulation, obviously, since we're looking at it from the top, but it's a high fidelity simulation, and the white areas are predominantly stars. The dark areas are predominantly dust and gas, and the red areas are stars forming. And we're 26,000 light years out from the center. We're orbiting the center of our galaxy at about 450,000 miles per hour. And it takes us 250 million years to complete one orbit. So if anybody has any guess as to where we are in this picture, this is where we are. We're out on the limb, 26,000 light years out. And the little inset there, you see a little blue circle. That blue circle is a 200 light year diameter zone that represents the area that our radio noise from radio, TV, cell phones, everything has reached since we've started creating radio. So basically, all the noise we've created 200 in the past 200 years. Unfortunately, there was a recent analysis looked at the intensity of this radio noise that we've generated, and they determined that it was well below the detection capabilities of an Earth-like civilization located on the nearest star. So if on Alpha Centauri there was another civilization like our own, we would still be silent to them, and they would probably be silent to us. So unfortunately, even though we're fairly noisy people, it fades out pretty quickly as we go into the galaxy. Going to the next step up, this is our local galactic group. And so you're here in the Milky Way. The Andromeda galaxy is 2.5 million light years away. And all these other little spots that you see there that are labeled are all various kinds of small galaxies or dwarf galaxies. We have one sort of smaller galaxy, Triangulum, which is a little to the left and down from Andromeda. It's the next biggest one in our little group, but this is 8 million light years, so fairly small. But we're heading towards Andromeda. And in fact, we're on a collision course with Andromeda. So in roughly 4 billion years, we're going to collide. And somebody did a simulation of what that would look like. And so in the top frame, you see what things are look like now. We just see the Milky Way. Andromeda is in there, but it's some faint little dot that is below the threshold of visibility. Come back in 3.75 billion years, and you're going to see Andromeda filling a fair amount of the sky. It's going to be a pretty big and very discernible galaxy. About 4 billion years from now, we're going to run into each other. And while these collisions, the stars don't collide, the clouds of gas do. They're much bigger. And so the whole galaxy will distort, twist around, and we'll probably do multiple passes of collisions. And in about 6 billion years, the two galaxies will merge into a single big galaxy, a spherical galaxy without a whole lot of dust in it. And so if you come back in 6 billion years and look at what's around us, it would be this big fuzzy ball without all the structure that we see in that top frame. Going even further, this is now where I showed you were before. This is the local group. And this is now 300 million light year diameter, and it's 2% of the size of the observable universe. And you can start to see that galaxies aren't uniformly distributed. That galaxies are in these clumps, and these clumps sort of don't follow any obvious pattern. And this is what is being called now the cosmic web. Galaxies tend to condense into these clumps, and then there are large voids where very little of anything is in between these clumps. And if you want to see a better picture of that, this is now a 1 billion year look back time. And the previous chart is in the yellow there. That's a quadrant that's 150 million light years in diameter. So this is the lower part there is what you saw on the previous chart, but this goes back now to 1 billion years. And still, this is a tiny portion of the universe. And so you can see here the cosmic web is that there are all these things that look like a spider web or a cobweb, and that's where all the galaxies reside. And this image here has 200,000 galaxies. And these are measurements made, this is not a simulation, these are measurements. And so you can see what our universe looks like. One thing I want to stress here is a subtle difference that people aren't told enough about. And that's critical to understand. The difference between the observable universe versus the universe. The universe is around 13.7 billion years old, and this has been established through multiple independent methods. So we're fairly certain that it's something around 14 billion years, maybe a little less, and there are arguments over whether it's 13 and a half or 14 and a half, but for the most part, around 14 billion years. Speed of light is the fastest anything can travel in the universe. So if there was an object in any direction that was further away from us than 13.7 billion light years, it would not be visible to us. The light from it would not have reached us yet, so we would know nothing about it. There's no way we can infer anything about it. So what astronomers call the universe is more correctly called the observable universe. And this is an approximately 27 million, it should be million light year or billion light year diameter sphere centered on us. And actually, this is one time when we really truly are at the center of the observable universe. The volume okay. So is that the entire universe, or could the universe be bigger? And it's actually impossible for us to know. To know, we would need to find a particle that travels faster than the speed of light to give us information on something we cannot see. And the universe is continuing to expand. So all these galaxies that we see out to 13.7 billion years have been expanding since the light left them. And so they now fill a volume of 46 billion light years, with us at the center, and the universe is continuing to increase. So what makes up the universe? Well, it's 5% matter, and matter is everything you see around you. All the stuff that you see is matter. 27% is dark matter, and this is stuff that appears to only interact gravitationally. It doesn't appear to interact, it doesn't give off light, doesn't do anything else other than it has mass. And so all the matter, if we combine dark matter and regular matter, it's 84% dark and 16% normal. But the big guy in the universe is dark energy. And this is a component of energy that seems to be being dumped into the universe, causing it to the rate of expansion to accelerate. And we do now clearly show a change in the acceleration, so something is happening. Dark matter has been known to astronomers and unexplained for almost 100 years, but it really has become sort of known to the public only in the last 20 years. When I was in graduate school, there were all kinds of discussions about, we didn't call it dark matter at the time. It was, other terms were used, but it was first found in the 1930s, or first established in the 1930s. Recent data has pretty much confirmed that it looks, well, I guess has reasonably suggested that dark matter is truly matter and not an error in our theory of gravity or some other misunderstanding. However, despite all the searches, we have still not been able to detect a dark matter particle. And data coming in, which is fairly meager, still doesn't support any one kind of object that could be the source of dark matter. Dark energy is we know much less about that. It was discovered in the 1990s, and it may be a force that's causing the acceleration of the universe. But it actually could be something else. It could be just basically a misunderstanding of a misrepresentation of gravity. Dark energy is not even understood well enough that we can document what it is. We don't know if it has always been in the universe, if it appeared at a different time. So very little information, so lots of speculation on what it is, but nothing with any firm basis. The Europeans launched a space mission called Euclid a few months ago, and it's now operating. And NASA plans to launch a mission called Roman in the next few years. And these are specifically designed to gather information on dark energy. And so hopefully when these two missions are up and operating another 5 or 10 years, we'll actually have enough data to start trying to decide what exactly is dark energy. So this is what makes up the universe in words. This is what makes up the universe in charts. So on the left is your traditional pie chart. It's the same thing. On the right was something I thought was pretty cute. This guy developed a recipe for a universe pie. And so it's 5% normal matter, namely the crust. It's 25% dark matter, and he has a chocolate cream cheese filling. And then 70% of it is blueberry pie filling. So if you want to make this pie and impress your friends with eating the universe, go to this website and he gives you the recipe. So what about the origin and evolution of the universe? What happened in the early universe is under active revision. The new data from JWST is greatly altering our conceptions of how the first stars and galaxies formed in those first 500 million years of the universe's existence. A lot of this data is really not fully understood, and it's changing as new observations come in or new analyses come in. One of the problems is that people make assumptions which may not be correct for the early universe, and so our understanding is certainly going to be changing over the next few years. It looks like our basic core understanding is still probably correct, but our details are certainly clearly not correct. And so this is going to be an active area of research for the next 5 or 10 years as Webb and others gather new information. But I want to point out that once galaxies form, they evolve over time. They do this mostly through collisions with other galaxies. So galactic cannibalism is the way of the universe. Small galaxies are eaten by big galaxies, and eventually they coalesce into larger galaxies. When these collisions occur, the stars are too tiny to collide, but the clouds of gas do collide. They compress, they form stars, multiple collisions between these galaxies eventually force all the gas into stars, and you have a large, usually spherical galaxy with lots of old stars and no new stars forming. And on the bottom is a time map of the universe. And note in particular, this is not a linear time scale. 13.7 billion years is at the left. And in the middle, it's about 13.4 billion years. And then it's today on the right. So what basically Big Bang forms, the universe is filled with hydrogen. Perturbations cause those to drop into some kind of structure. We don't know anything about that. We actually have no data on that. Eventually, the first stars form, and that's when JWST can start seeing stars and seeing galaxies and start giving us information on what happened at that time. And the white box there is the area that JWST can cover. And then all the other telescopes that we've talked about and built can see the rest of the universe. So right now, the James Webb Space Telescope is filling in that white box and going to be supplying us with information on what's happening there. And then at the very bottom, FarView, this mission that I'm working on, which I'll talk about briefly, in a few charts, we'll start looking at how did these structures actually first form. So status of our current knowledge. We're actually beginning a new revolution in thought. A lot's going to change over the next 10 to 20 years. And this is new data coming from the James Webb mission and Euclid now, others in the next 5 years. All these big telescopes coming online are going to supply new information. These facilities will certainly rewrite our science books and hopefully provide us with new insights into how the universe came into existence. What is dark matter? Does it really exist? What is dark energy? Does it exist? A variety of current other mysteries. As with any revolutionary period, what we think we understand is highly dynamic. Interpretations of new data change fairly rapidly, and certainly on a yearly time scale, all kinds of things change. So my recommendation to you is, at least today, be skeptical. Watch over the next few years as our understanding starts to transition to a new, somewhat consistent level of understanding. And this happens, Liz said I was on Hubble at the beginning, and this happened with Hubble. The first 2 or 3 years after Hubble, there were all kinds of rewriting of how we thought the universe worked, and that settled out after about 5 years. And while we're still improving with Hubble, big changes don't happen anymore. And that's it for this section. So anybody have questions on this section? Again, Jim, his question is, the image showing what the merged galaxies M31 and Milky Way would look like seems misleading. I would think that a number of stars visible to the Earth would approximately double. So why would that overall foggy look obtain? You're gonna have to actually give you more images in between. And what he was trying to show with that is that, and I too would have had a more filled sky, but the galaxy will be a lot bigger. And so they won't be as dense. And if you look at our Milky Way, there's a band of light, but then lots of dark areas where we're outside the plane of the galaxy. This will be a spherical galaxy. The stars will be relatively uniformly distributed around us. What he shows in this is what he had us position somewhat outside this spherical galaxy, so that he could show that it was not looking like the Milky Way. Main point was he wanted to show that it was not a disk galaxy, but a spherical galaxy. But you can go look at the website. He's got some fairly interesting pictures. But yeah, it's a question of interpretation. So, but I agree that I may have done it differently. Question from the chat. What is the biggest discovery change you anticipate with these new telescopes bring about our understanding of the universe? Probably the biggest change is going to be, what is dark energy? And the reason I say that is that there still is a fairly active debate that dark energy is really an artifact of we're using the wrong formula for gravity. So this is something like what happened around 1900, when we had started gathering enough information that Newtonian gravity was found to be wrong. And so it was discarded, and a relativistic gravity came up. And so that's what I would guess is going to be the next big discovery, is really what is dark energy. And so once we understand that, and if we say that is really due to some misformulation of gravity, then that's going to have to percolate through all of the things that we do. And then fairly close behind that would be dark matter. I mean, we still are looking for a dark matter particle, and without that, it still is a mystery. And then I'll talk about a little bit later, finding true evidence of life outside the Earth will be certainly a big factor. And so Jim just added another question that says the other images seem to be from the Earth. Yeah, these are all from the Earth, but it's where you put the Earth. And so he puts the Earth outside because his big point was he wanted to show that we would live in what's called an elliptical galaxy, or essentially a spherical galaxy, not a disk galaxy. All right, any more questions? All right, let's move on. So searching for life in the universe. First thing we need to do is define it. And this is difficult because we only have one case, Earth life. So what NASA is using as its definition of life is a self-sustaining chemical system capable of Darwinian evolution. Most life on Earth actually produces molecules and compounds that do not occur through inorganic processes. So we look for these. And besides looking for these chemicals, we also look for something that is non-equilibrium. In other words, a molecule or a compound that we do not think can be generated by known non-biological processes. The laws of physics and chemistry are the same everywhere. So if we see something unexplained, one possibility, and I stress it's one possibility, is that it's been created by life. The one thing we have assumed, which is an assumption since we've not, we only have our one case of Earth life, is that water is required for life. And so all of our searches tend to be focused on places where water is present. So within the solar system, there's lots of places that people have thought about life. Mars, we've been looking for life on Mars since the 70s. Right now, there are caches of Martian soil that are being stored on Mars, pulled up by the rovers, and there are going to be missions late in the late 20s to bring them back to Earth, arriving here sometime in the early 30s to be tested for signs of life. Europa is our next best choice for life, and it is a moon of Jupiter. And a mission called Europa Clipper is going to be launched later this year, and it will go there and start surveying it and trying to find a spot for a landing to test if there's life on Europa. And the reason we think there may be life on Europa is that it has an icy crust, but underneath that crust is about a 60-mile deep ocean, so much deeper than Earth's ocean. And we think at the base of this ocean is going to be things like the thermal vents on Earth that will be supplying energy. And so we think that life may abound in this ocean. And eventually there will be a NASA mission that will send a probe into this ocean to see if it can see signs of life. Enceladus is another icy moon, and it's basically a miniature Europa. Venus a couple billion years ago was very Earth-like. Probably had temperatures not that different from Earth, oceans, other things, but runaway greenhouse effect raised the surface temperature to over 800 degrees. And so there's no life on the surface, but there is evidence that life may exist in the clouds. There are changes in the Venus clouds, and clouds are very similar pressure and temperature to Earth. And so 3 missions are planned to travel to Venus in the 2030s that will hopefully check out to see if there's life on Venus. And Titan is the big moon of Saturn. It's too cold for life to exist, but it may contain a lot of precursors of life. And so it's bigger than our moon, has a denser atmosphere, and lots of hydrocarbons. And NASA's planning to send a mission there, launching in a few years and getting there in the early 30s. And its primary payload is actually essentially a helicopter. And it will go to dozens of spots on Titan looking for prebiotic chemicals and see if we can figure out how life began in our solar system. As far as the planets, exoplanets or extrasolar planets, you'll hear that word a lot. These are just planets that are orbiting other stars. First one was found in 1995. As of January 10th, a few weeks ago, there are over 5,500 confirmed exoplanets and 7,000 likely exoplanets. We only sampled a small part of the galaxy, so if you take a guess, given this small sample, how many planets there are, there's going to be a few trillion planets in the Milky Way. There's as many as 6 billion Earth-like planets in our galaxy. As of right now, we have 4 sort of broad classes of planets. There's the gas giants, things like Jupiter, and they're about 30% of the planets that we know of. Neptune, like probably the most common, they're about 35%. Things called super Earth, which we do not have an analog in our solar system, are things that are a few times bigger than the Earth, but likely still rocky. They're also about 30%. And then us, our little terrestrial planets like Earth, are a tiny 4%. But this may be an underrepresentation because we still don't have the technology to really detect terrestrial planets. So my guess is that over the next 15 years, this percentage will rise as our technology lets us detect Earth-like bodies. So detecting Earth-like planets, as I said, is extremely hard. This image here on the right is a artist rendering of potentially habitable planets, plus Earth in the upper right and Mars in the upper middle. This is planets that we think at least have the potential, given their location with respect to their star and their size, of having life. But we really have no way of detecting life on these. And we're working on instruments that probably in 10 to 15 years will be able to actually at least give us our first crack at this. We have developed methods to determine whether the body is rocky, an ocean world covered mostly by water, or gaseous like Neptune. So that's being refined. But we still really don't have the ability to detect life on other planets. Even with regards to the planets themselves, we're finding a much wider range of types of planets than we had thought. So basically, we're still learning. We still don't know a whole lot about planets and how they form, but we are learning. And then finding reliable signatures for life in these bodies is extremely difficult. JWST may have detected our first unexpected molecule, dimethyl sulfide, in the atmosphere of an exoplanet, but it's a pretty low confidence detection, so it needs to be confirmed. And even if it is to confirm, it's not certain that you can't make dimethyl sulfide through non-biological processes. So those are both being studied. So basically, right now we still are clueless as far as searching for life, but hopefully that will change in the next 10 to 15 years. So with all these planets everywhere, 6 billion Earth-like planets, where is everybody? And Enrico Fermi, a physicist in 1950, in a casual discussion with some other physicists about space travel, said, where is everybody? And that became the Fermi paradox. And so from what we know about the universe and the abundance of planets, life should abound. Given the long time scales and lots of life, we should have had some evidence of life detected outside the solar system, but nothing has been found. So why? What's missing? Lots of possibilities. Life of any kind may actually be much harder to develop, and we'll start getting some information, or even if it develops, it may not survive. So that's a possibility. And maybe that life is actually easy to form, but intelligent life is very difficult. That's certainly a possibility. Also, intelligent life may form, and may even form frequently, but self-exterminates through wars, environmental disasters, disease, long before it can expand into the stars. And unfortunately, we'll be experiencing that ourselves, and so we'll see if we survive the next 100 years. And of course, intelligent life develops often, but they're hiding from us or abducting us. So those are certainly all possibilities. So what lies ahead? Humankind's expansion in space. Commercial entities and governments are developing concepts and hardware for sustained human presence in space. These include both scientific research, factories, labs, observatories, and of course, tourism, hotels, and all that kind of stuff. NASA is leading an international effort called the Artemis program with for-profit companies, including my company, to develop a permanent presence on the moon. And China is pursuing a similar path. The next big jump in science missions will be lunar science-based missions. These will probably start appearing in the 2030s. So leveraging the quest for a sustained presence of the moon, NASA is looking at building low frequency radio telescopes on the far side of the moon. And the reason they're done on the far side of the moon is to shield them from all the noise that the Earth generates. These stars would study the universe before stars form, so mapping out these hydrogen concentrations, and also looking at some of the exotic physics that may have occurred shortly after the Big Bang. FarView, the mission that I'm leading, is one of these. It consists of 100,000 dipole antennas spread across 80 square miles of lunar surface on the far side of the moon. One of the many unique things about FarView is that it would be built entirely robotically from metals extracted from lunar dirt. So we scoop up the lunar dirt, we pull the metals out of it, we put them into another device that manufactures antennas, power lines, solar arrays, and build our observatory that way. This is what FarView would look like on the moon. The silvery white stuff are the dipole antennas. The darker stuff are power lines, and it's a zigzag pattern to give us a better representation of what we're looking at. And hopefully this will start being built sometime in the late 2030s. And that concludes my talk. So thank you, and any questions?
Ron, why don't you go ahead and stop sharing your screen?
Did that?
Yeah, hi. That was awesome. Anybody have any last questions for Ron? And I am quickly going to drop those links into the chat, which I forgot to do. So sorry, but I will do it now. Any questions for Ron? I love that you included the universe pie recipe on your links, Ron.
It's actually an interesting recipe.
Oh, have you tried it?
I haven't tried it yet.
Okay. Okay,
And
well, we'll just give it
Jim
a couple
Hammond,
more
who's
minutes.
online, Jim Hammond, who's online, can tell you about his black hole cookies that he made.
Oh my. Okay. All right, there are the links, but like I said, I did put them on the event calendar so you can take your time and access those. Oh, look, we got a question. Jim wants to know if you've watched any of For All Mankind.
Not yet. People say I should be watching that, but I have not yet watched it. Part of the problem is in leading this study of the FarView telescope, I've discovered that at age 75, I'm not as active as I used to be. And it's taking up a lot of time. So
Yeah, fair. And then Anna would like to have you share with us a little bit about your education, history, and how you came to study what you do.
I'm one of these people that from at least as early as I can remember, so around age 5, I was interested in space and all that kind of stuff. And my older sisters would take me to the library and always check out space books. So there was always some level of that. And the library was my play area, so I always wanted to go to the library. And as I evolved, my parents weren't really oriented towards science, and so they didn't understand that astronomy was actually a profession. So I ignored all the discouragement and then went off, got a bachelor's degree from University of Michigan, PhD from UCLA, and then began my journey of started off working satellites right out of graduate school, actually before graduate school, and stayed in the satellite business pretty much the whole time. I have done some ground-based observations. Moved around with jobs, got offered a job by NASA, stayed there for 12 years, decided to see what industry was like. Went to Northrop Grumman for another 12 years, and then retired, got bored, and went back to work.
That's awesome. I have a question for you. For you personally, what's the most gratifying component of your work? What made you unretire? What keeps you motivated to keep doing the work?
It's the quest for knowledge. I mean, if I look at what excites me it's those eureka moments. Oh, now I understand. I see how this works. That just really gives me the reward that I want from all of this. And I think this is true of most scientists. It's really becoming aware of how something works at a level where you can actually tell people this is what's going on. That is really the thing that drives me.
And I'm also with a follow-up question, with all the technology that, I mean, what about the new scientists, the young people just coming up? Are you confident that they're going to be able to, I mean, do you see a spark in them that's going to keep
Oh yeah.
moving
So in fact,
forward?
actually, I was at a large astronomical conference the first week of January, and we presented results on Farview. And there was a really interesting dichotomy. The older astronomers were very suspicious. We've never done this on the moon, all this kind of stuff. Anybody who approached me that was under 35 was just totally excited about this. And how can we learn more? How we do things? So yeah, there is a new surge coming in because, and I think part of it, it's now a little bit more of the Wild West. There's a lot of opportunities, a lot of new things, and all this kind of stuff that's happening. And so younger people see more opportunities and more ways to really advance. And so it's really been nice to see because there was a period of time where things were getting pretty moribund, and that's gone. This is now a new era where, as with any establishment, challenging the status quo is always difficult. And now the status quo has disappeared. There is no status quo. So you're free to propose what you want and debate it and discuss it. And it's very exciting. And also, there's a new message, a new question from Marilyn. Will the moon supplement JWST and other current information, or will it provide totally new information? Mostly it's totally new, but there are areas where it will supplement. And so, Farview sensitivity overlaps a little bit with Webb, but since they're looking for stars and we're looking for not stars, it's a little different, but they do overlap and combine. I mean, this is the issue with combining all the knowledge from all the various domains is that we really found out that you really can't understand the universe by looking at it through a soda straw. You really got to look at the whole universe to understand what's going on. And each of these contribute their piece. And this is part of the reason why, if you look at published papers from astronomers in the 1950s, it was 1, 2, 3 authors, something like that, because they would just work in a little area. Now 50, 60 authors are not uncommon, because if you're going to work in everything from gamma rays to low frequency radio, one person can't do it. You've got to have a team.
Yeah. I remember, I'm just looking for your reaction when you first saw the pictures, the first pictures from the James Webb Telescope. How did you
Yeah.
feel when you first saw those? Was
Oh,
that
that was
unexpected
amazing.
or was totally what
Well,
you thought?
yeah, it was. Well, also I knew a large number of people who worked on it. A number of them worked for me. And so it was nice to see them with all this effort they put in, with all of the criticism it got before launch, to now succeed, to see that success and to see it working so perfectly. And it really was truly amazing. Even behind the scenes, very, very little went wrong. And so it was just one of the smoothest launches and commissioning and startups of any satellite that ever been built. And it was just nice to see that, given the huge effort that went into developing this telescope.
Yeah, the pictures, those first pictures that I saw were stunning. And I certainly don't have, didn't know what I was looking at or what I would have seen prior to the Webb telescope, but boy, they're sure gorgeous.
Yeah.
Okay, any last questions for Ron? Okay, well, we sure appreciate you sharing your knowledge with us this afternoon. All
All
right,
right.
everybody, have a great rest of your day.
Bye.
Thanks.